so simple to imagine. We begin and we will go it slowly, step by step, and then you can imagine what I want to explain to you. First, I will explain to you what is a coordinate relative to a basis. Now, suppose that B consisting of V1, V2, Vn. Suppose that B is a basis for a vector space V, and X is a vector. X is a vector inside the space V. Then, as we know that B must be linearly independent and B must be generating set. By generating set, I mean X can be written as a linear combination of the vector here. Means X will be C1 time of V1 plus C2 time of V2 plus Cn time of Vn. But because V1 up to Vn are linearly independent, then X can be written in only one way like that. It can be written uniquely like that one. You cannot write it in another form. So the x1, x2, and xn are determined by x. So the number of the scalar c1, c2 up to cn will become the coordinate of x relative to the basis b. So that is the name for the coordinate. And because it is unique, when you are given x, you have unique c1, unique c2, and unique cn. So that x equals c1 v1 plus c2 v2 plus cn vn. Then because of that, c1, c2, cn will become the coordinate of x relative to the basis b. In Vietnamese, I am sorry if some of you did not understand. Cái ông x này chỉ viết được một cách duy nhất ở cái dạng tổ hợp tuyến tính của các cái V1 cho đến Vn như thế này thôi. Có nghĩa là các cái hệ số C1, C2 cho đến Cn được xác định duy nhất bằng chính cái vector x. Vì thế các cái số C1, C2, Cn được gọi là tọa độ của x đối với cơ sở B. Okay, let me continue. Usually the coordinate of x will be write in the form of the column matrix, and we call it the coordinate matrix, and it is here. It will be written in this form, and we call it the column. We call it coordinate matrix or the column coordinate. And in order to specify that is a coordinate relative to the basis b, we put the b here as a subscription here, x b, like that. And the next one is an example. Suppose that we are considering the 3 space R3, and in R3 we know already that it has a standard basis that is S consisting of 3 vectors 1 0 0 0 1 0 and 0 0 1. And now we are given a vector x with component -1, -2, 1, and 3. Then we need to find the coordinate of the coordinate column or coordinate matrix of x. How we can find it? We have x to be that equal -2 times of the first one, plus 1 time of the second one, and plus 3 times of the last one. So the coordinate will be -2, 1, and 3. -2, 1, and 3. So that is the easiest way, easiest examples, because we consider only the standard basis. We can consider the non-standard basis, but however, before that, I can show you something. The same vector, the same point in a space will have different basis relative to different bases. Here is an example. Please look at that. On the right hand side and the left hand side, we have the same coordinate plane and the same point or the same vector m. The m is here. That is the same vector, the same point. On the right hand side, oh sorry, on the left hand side, we consider the standard basis. It is here. It consisting of U1, U2. It is a basis because it is a linearly independent and is a generating set for the coordinate plane. And in this basis, the point or the vector m has coordinate 6, 4. You can count here. 1, 2, 3, 4, 5, 6. And up here, 1, 2, 3, 4. So now in relative to B, the M has coordinate 6, 4. Now on the right hand side, we take another basis. Another basis I denoted by B prime, consisting of V1 and V2. V1 and V2, they are linearly independent and generating sets also. So because of that, B prime is again a basis for coordinate plane. But in that basis, it's a basis B prime. The coordinate of M now is C2. C2. Because M equal 3 times of V1 plus 2 times of V2. So you see, the same point or the same vector, but in different basis, we have different coordinate. That is one important thing. Now I consider, okay, in 3 space R3, we consider the new basis I denoted by B prime. It has 3 vectors U1, U2, U3. U1 to be Z, U2 to be Z1, and U3 to be Z1. And that basis is non-standard basis. Then we need to find the coordinate of Z1, of X here. How we can do it? Once again, we have to solve the system of linear equation. To find the coordinate means we need to find the number C1, C2, C3, so that we have the equality X equals C1 of E1 plus C time of C2 time of U2 plus C3 time of UC. We write it here. We substitute X into here, U1 but into here, and U2 into here, and UC to here, and we get that one. Then, because of that, we get a system of linear equation like that one. And it means that we take the coefficient matrix and multiply by the columns of unknown of variable C1, C2, C3. We get that column. And we can solve it by using Gauss-Jordan elimination. We get that one. So get that one means our coordinate will be 5, -8, and -2. Yeah. So that is the way we find the coordinate of any vector if we are given already the basis. And in this example, the basis is non-standard. So now you will have a problem of change of the basis. As we have seen already, of the same vector, but in different basis, we have different coordinate. So if you are given a vector V inside a vector space, and suppose that we know already the coordinate of vector V relative to one basis B prime. But if suppose that the space has another basis D, and you are required to find the coordinate of the same vector V, but now relative to a basis B, how you can do it? How you can do it? And the next example will show you. the easiest case. Now we consider an example. We consider a space of the base of two dimension, means we have two different bases. B consisting of U1, U2, and B prime consists of U1 prime, U2 prime. Now, first of all, because U1 prime is a vector inside V, and B is a basis, so U1 prime will have coordinate in B. The coordinate of U1 prime relative to the basis B equal A and B. So similarly, the coordinate of U2 prime relative to the basis B will be C and D. So I denote it like that. Now, that it means that U1 prime equals A times of U1 plus B times of U2. And similarly to that, U2 prime will be C times of U1 plus D times of U2. So that now we have a presentation of U1 prime and U2 prime in U1 and U2 as a linear combination of U1 and U2. Next, suppose that V is a vector inside V, and suppose that we know already the coordinate of V in B prime, and suppose that they are K1 and K2, that is coordinate of V relative to B prime. What does it mean? It means that V equal K1 of U1 prime plus K2 of U2 prime, because B prime consisting of U1 prime and U2 prime. But in the previous slide, we know already that U1 prime equal that and U2 prime equal that. So because of that, we get V equal that number as that vector. Now we regroup the vector U1 with U1 here, U2 with U2 here. You get that equal K1A plus K2C times of U1. And then K1B plus K2B times of U2. That is, now the presentation of V as a linear combination of U1 and U2 to be that means the coordinate of V relative to B, relative to the basis B will be Z1 and Z1. It means that that number is the first coordinate of V relative to B, and here is the second coordinate of V relative to the basis B. So we write it in the coordinate column, the column coordinate like that. But once again, if you remember, that number is nothing but the product of two matrices. The first matrix is A, C, B, D, and the second matrix is a column K1 and K2. And we can, if you remember, look at that. The first column here is exactly the coordinate of U1 prime relative to the basis B, and the second column here is the coordinate columns of U2 prime relative to the basis B, and that one is exactly here. That is the coordinate columns of the vector V relative to the matrix B prime. So that is the examples. Is not so complicated to follow. Now I want to. Here is some example, simple. Now I can generalize it for the space of any dimension. Here we are going to define what we call transition matrix from B prime to B. Ma trận chuyển cơ sở từ B phẩy sang B. That is the name in Vietnamese. Suppose that we are given a vector space V of the dimension n, and V has two different bases B and B prime. B consists of U1 up to UN. B prime consists of U1 prime up to UN prime. That is two different bases for a vector space V. Now, we denote V sub B, that is the coordinate matrix or the coordinate column of V relative to B. And similarly, the V sub B prime is the coordinate columns of V, but now relative to the B prime. So here B is here, B prime here is a B prime. Then, if we denote it like that, we will get the following relation between VB and VB prime. VB will be P multiplied by VB prime. So what is a P? P is a matrix. P is a matrix. It is given by that thing. It has n columns. The first column, the second column, and the n column. And those column is exactly the coordinate column of U1 prime, U2 prime, up to UN prime, relative to the basis B. Here, I write it here. B to be that one. And that matrix P will become the transition matrix from B prime to B. Ma trận chuyển cơ sở từ cơ sở B phẩy về cơ sở B. Bên phía công thức này, bên phía trái là các tọa độ của V theo cơ sở B. Bên phía phải là tọa độ của V theo cơ sở B phẩy. Vì thế công thức này gọi là chuyển cơ sở từ B phẩy về B. Cái đó được cho bởi cái công thức là nhân nó với một ma trận P. Chính như ma trận P định nghĩa như thế này được gọi là ma trận chuyển cơ sở. So we can observe that in the previous slide, the role of B and B prime are the same. Hai cơ sở B và B phẩy có cùng vai trò như nhau trong cái định nghĩa này. And because of that, we can define a transition matrix from B prime to B and from B to B prime. We can do it by the same way. And here is some claim. Suppose that P is transition matrix from a basis B prime to a basis B in AN. Then the first claim says that the matrix P is invertible. P is obviously a square matrix of psi n by n. But now we claim that P is invertible. The second one. Now if we consider the transition matrix from B to B prime. In the previous slide, we defined the transition matrix from B prime to B, but now from B to B prime. So the transition matrix from B to B prime is exactly P inverse. Is a P inverse. It is the inverse of transition matrix from B prime to B. So we can summarize everything we study from the beginning in the following. Suppose that B consists of n vector U1 to Un. B prime consisting of U1 prime up to Un prime. And V sub B is the coordinate column of V relative to B, and V sub B prime is the coordinate column of V relative to the basis B prime. Then those columns VB and VB prime relative to each other by the following formula. VB equal P multiplied by VB prime. or VB prime equal B inverse multiplied by VB, and P inverse can be computed by applying those formula. So that is what I summarize here for you. Then once again, one of your exercise, one of your tasks, that is, please find transition matrix from B to B prime or from B prime to B. How you can find it? Suppose that you are given a vector space together with two different bases B and B prime. How you can find the transition matrix? So here is the same way. The way to do it, and you will see it is quite similar to the way you find inverse matrix by using Gauss-Jordan elimination. Here, the way you do is follow. You write B first. You write B, and then on the right side of B, you write the second one, B prime. So we have two bases and put it in the columns. Yeah. Then you apply Gauss-Jordan elimination. Gauss-Jordan elimination. On that, you try to make the first part here transform into identity, which is I and A. Then the second part, I mean the B prime part, will be changed into something, and that something is exactly what we call the transition matrix from B to B, from B prime to B. And now, the best way, that is, we look at an example. Suppose that we are given B like that and B prime like that. They are two different bases for R2. Then you have three things to do. The first one, you need to find the transition matrix from B prime to B. Then the second one, that is, suppose that we know already the coordinate of V relative to the basis B prime to be that. Then you are required to find the coordinate column of V relative to the basis B. And the last one, you need to find the transition matrix from B, back from B to B prime. That is, we have three requirements to do. And the first one, we apply what we call the method using Gauss-Jordan elimination. We put B like that, and on the right hand side, we write B prime. Then apply Gauss-Jordan elimination, you get that thing. The first part now becomes identity. So the second part is exactly the transition matrix we need to find. And here it is the transition matrix from B prime to B. And the second one, now whenever we have a P, we can apply the formula to find to change the coordinate. It is here. V, the coordinate column of V relative to B equal the matrix P multiplied by the coordinate columns of V relative to B prime. So finally we get that result. And the last one, you can verify that one. But however, to the last one, that is the part C. Once again, now we change the role of B and B prime. So it is here. Instead of writing B here and B prime here, we switch it. B prime now on the left and B on the right. And then once again, apply Gauss-Jordan elimination. When the first becomes the identity, the second part will become that vector. And that vector is exactly P inverse. That is a P inverse. And so because of that, P inverse to be that one, and you can verify that thing. So that P inverse has name transition matrix from B to B prime. The other one is some more example for you. The coordinate, the representation in P3. I need to repeat to you that what is a P3? P3 of X, that is a space, that is a vector space of on polynomial of degree less than or equal to 3. Không gian tất cả các đa thức mà có bậc bé hơn hoặc bằng 3. Then we know that it has a standard basis consisting of 1x, x2, x square, x cubic. And suppose that you are given a matrix, a polynomial P like that, and you need to find the coordinate of P according to S relative to the basis S. How you can do it? Okay, write it like this way. Then you get that thing. And the second part, you need to find the coordinate of P, but now relative to a non-standard basis. Non-standard basis is here. And once again, that is some calculation, and you get the coordinate column of P in B prime. I mean in them is nothing, because here is 3, 0, minus 2, and 3. So we have that. Again, the last slide of the lecture number 4, that is, suppose that in M2 by 2 we consider the standard basis, and you are given a matrix X, then how we can find the coordinate of X relative to the basis, standard basis B? Again, we write it in the equation like that, and we can find the solution is 5, 6, 7, 8. That is coordinate of X relative to the basis B equals 5, 6, 7, 8. So that is on what we need to study in the lecture number 4. So now we have a short break, and then after the break we begin with the lecture number 5. I upload the slide of the lecture number 5 already on the Moodle. So we stop here. Oh, I'm sorry, not stop here. We have a break now for 5 minutes. Sorry.